Let's take an example where we have A, B, C, D with the indexes 0, 1, 2, 3, and you have two operations being performed here. The first one is deleting the character B, and the second one is actually adding a character over here between these two, and that will be character E. Okay, so whenever we are making these operations, actually we have something implicit in it, and that is the index information. Because even when you say delete B, which B are you talking about? It could have more B's later on. So which B is it will be defined by the index of that character. So in that way, you don't actually need to mention the character, you just need to mention the index that you want to delete. That is the operation. Similarly, where do you want to add this E? We don't know whether we want to append it at the end or you want to add it in a specific position. So index has to be mentioned. In our case, the index is, as we said, index 2. So all characters after in and after 2 have to be pushed to the right, and similarly delete index 1. Okay, so the results of these two operations are A, C, D, indexes 0, 1 and 2, and similarly over here you have A, B, E, C, D, indexes 0, 1, 2, 3, 4. Now how can we reconcile these two copies? There's a naive way of doing it, which is just perform the opposing operations on them. Okay, and we are hoping that we have the same document, but let's see. So that would be deleting at index 1, and the other would be adding at index 2 the character E. What happens here? If you run this operation, it comes to A, C, and then the character, which is E, and then D. And if you delete at index 1, you have the final result A, E, C, D. Okay. So these two copies are actually not matching. That is the problem that we have. The reason this is happening is because when we are saying delete a character at index 1, what's effectively happening is that all the other indexes ahead of it are being shifted behind by one position. So when we go back in time, over here we are basically behind in time according to this copy. So when we are going back in time and we say, please add a character E to position 2, what should effectively happen is we know that all the indexes after index number 1 have been decremented. So what we should do is we should add this E at position number 1. If you do that, then you can see that at position number 1, when we add, that comes out to be A, E, C, D. Okay, position number 1 is over here, so you push these two guys ahead. Similarly over here, when we had pushed E to position number 2, C and D had gone ahead. So you have this copy, and this copy is fine. Okay, so we need some sort of an algorithm which tells us that when you're deleting characters, all the indexes ahead have to be pulled back by 1. So the subsequent additions also have to be pulled back by 1. There needs to be some sort of an algorithm which is telling us to do this. Also, when you're adding characters, you are effectively pushing ahead the indexes of all the characters ahead of E. So if you have another add at a particular index, that also has to be pushed by one character. So taking all that in consideration, there's a very famous algorithm which is also equally complex called operational transform, and this is most likely what is running in the heart of the Google Docs reconciliation algorithm. Operational transform is something which gives us an operation over here, an operation over here, and the inverses of those two operations. So effectively you had these two original operations, and these two will be the inverses that you need of the corresponding operations. Okay, so if you have operation X and Y, you need effectively the operations X inverse and Y inverse to be applied on the opposing documents, right? Once you have them applied, then you'll get the same copy. That's the general idea. It's a very rough overview. One way to implement it in a Google Docs kind of thing is to decrement indexes of all subsequent addition operations which have had decrement operations before them. Okay, so and similarly, like we said, addition is going to be incrementing the index. The reason I'm not going into too much detail over here is because the operational transform is very, very involved. There's a lot of edge cases, and in my opinion, there's no way that this can be asked in an interview. Knowing about it is one thing, but actually performing it is a little beyond scope. Okay, the second algorithm that you can use, which is much simpler but still is not expected to be answered in an interview without reading a few research papers, is called a CRDT, which stands for conflict-free replicated data type. And the idea in a CRDT is that you have a distributed system. So you have multiple clients, multiple servers. I mean, there is no such thing as a client, really. It's more like a peer-to-peer protocol where there's a copy over here, copy 1, copy 2, copy 3, and they reconcile with each other by actually sharing the data that they have. And they're not really, bound by a particular server, which is the source of truth. While in the operational transform, it makes more sense to have a server. That's one of the reasons why Google Docs is actually using this under the hood, most likely. While in a CRDT, it's much better if you think like in terms of blockchain, where there is no central authority to tell you what is the current version of this document. What's going to happen is all of the people are going to be sharing the data that they have, and eventually it's going to be a consistent system. Okay. CRDT is actually gaining a lot of popularity. There are certain applications where CRDT makes a lot of sense. But like we said, we are not going to be getting into the algorithm deep. We are just going to be understanding that these are the complexities that we have and why taking locks on a large document is not a great idea. Finally, another cool algorithm, which is highly unlikely to be asked in an interview, is for finding the differences between version A and version B of a document. Okay, so if you have two versions of a document, they have different contents. You want to find the diff of the two contents, very similar to how Git gives you a diff. Then the algorithm that you're looking for is called a Myers algorithm. Again, there's a link in the description below for all of this, of course. The reason why I'm not getting into Myers algorithm is, again, it's a little complicated. It's like edit distance, but it's a little more complicated than that. One idea that you can actually use if you're asked to find the difference between two versions, that being a feature, then you can talk about the longest common subsequence. This is an interesting algorithm because it tells you what is the longest common subsequence between two strings, so basically two documents. And once you have that, if you delete that, then you just have differences in the two documents. That can be represented as a difference. It doesn't do very well in practical contexts, but I mean, it's an idea which should work in a short interview. In the real world, of course, you can mention that I'm going to be using the same algorithm that Git uses for finding differences.